Okay. So one of the things that you'll notice on the Comets lab that you're about to get back, almost all of you got it right, except for the orientation of the tails. Tails were wrong. And about half of you got it right, which means that you just talked to someone. And half of you just drew what you thought looked cool, which means that you didn't even think to like ask someone. So let's remember that me and Caesar are here to help your learning outcomes. Okay? So let's use me. Let's get 100. What's the point? Let's just get 100 on everything, and then I give everyone A's. You get little stickers and coins, and everyone's happy.
You said those were stopping. Yeah.
Okay, well, maybe I'll invest. You invest in your education, I'll invest in coins. Yeah? Good plan?
Aren't you my investor?
No. What's this? Oh, what? Yeah, it's a comet. Good. Is that it? That's the only thing you see? Blue and cyan. Oh, okay, cyan. Blue and cyan. So there's two different colors here, and they look like they're separated. Right? We'll talk about that. Oops, this is old slides. Let me see if I can. Okay. What's that? It's a rocket. This is actually from Vandenberg. This is from last semester, but I took these photos when I was driving home, so you can see like that starts, and then that's it later.
Yeah.
No. So what happens here is it releases gas into the upper atmosphere, and the gas condenses clouds. And as the sun goes down, these really high altitude clouds can still reflect light down to you. So remember we talked about noctilucent clouds? Yeah, you all remember? Yep. Okay, some of you remember. Here's another example of them. Okay, is this a comet?
No.
Could be, maybe. Raise your hand for comet. Huh? Raise your hand for something else. What do you think the something else is? Asteroid. What's an asteroid? Right, floating rock in space. What makes you think this is rock?
The texture.
Yeah, the idea that if I lived it, it would feel like a rock, right?
I don't want to fight it.
I don't want to bite it, right? Okay. Anything else about it? Color, yeah, gray. Could be a black and white color, so we don't really know.
It's very round.
Not very round. So what does not very round tell you? Not a planet, but
Not big enough.
not big enough to be round. Remember, that's the idea of the beginning of what a planet definition. Okay, what else do you see? Craters. Okay, so it does in fact like collide with stuff big enough to have craters. Anything else?
Yeah.
What?
Not it. It looks like it's not smaller homes.
Okay, so you think maybe it looks like lumpy, like other rocks look lumpy? Okay, any like lines you see?
Yeah.
That's kind of weird, right? Fractures. I don't think about it at all, right? Never. This is my first time ever thinking about it. Okay, so those are asteroids. Asteroids are leftover pieces. We talked about the Kuiper Belt. This is the same type of leftover junk, but it's in between the orbit of Jupiter and the orbit of Mars. And probably Jupiter is the reason why this junk never formed into a planet, and there's no other asteroid belts in the inner solar system. Right? There is no asteroid belt in between Mars and the Earth. There's no asteroid belt between the Earth and Venus, and so on and so forth. Okay? So there's a lot of space in between Jupiter and Mars, and no planet ever formed it. Okay? So all we have are these little rocks. Okay? Here's the sizes. That's the moon to scale. That's Ceres. Remember I said Ceres had that little bright dot on it? We showed that in the KBO talk. And then there's 4 other ones. Look how great they're named, okay? Asteroids are so cool. So Ceres, 1. 2, Pallas, 3, Juno, 4, Vesta. Well, we're gonna see 4 or 5 later, but but do you get the why they're numbered like this? Just how we found them, the number we found them in. When we find a new asteroid, you get a longer number. So here, for example, there's Vesta. Sorry, there's Ceres. The moon's up here. 2, 3, Vesta, 5, 6, 7, 8, 9, 10. Right? And you just keep going and you keep going. And this will be important when we look at the next image. Okay. So let's keep in mind, this is Ceres. There's Vesta. It's a picture, a real picture of Vesta, not a fake one. There's 21. Lutetia. Kind of close. Kind of close. 253. Mathilda. 243. Ida. And then the fun one, he has a little friend. You can't really see it good, but there's a little dot right there. That's not a mistake. That's Dactyl. Okay, so it's an asteroid, and the asteroid has an orbiting little asteroid. That's Dactyl. You have 433 Eros, Gaspar, Steins, and Itakawa. So this tiny baby dot down there, you can see how big these numbers got now, right? Okay. All right. So which of these are round? Vesta, kinda. What about Lucia? No? Not really. Okay, so this is basically the idea of some minimum radius necessary to be large enough in order to become circular. And it's that big. Okay. Cool. Nice math. Thank you. Okay, so let's zoom in now. We're going to look at these small ones here. Think about that. Okay. You have Dactyl, that tiny dot I told you about. There's Lucia. Look at those surfaces. Similar, dissimilar to what you expected it to look like. Similar. Okay. Smoother than you expected it to look?
Yes.
All right. No, not smoother. You expected it to be this smooth? Okay. All right. Not all of them are circular, as you can see here. Some of them are long, they're elongated like this. And as we look down on the right-hand side, I put a little line here, because these are kind of different. We'll talk about those in a little bit. All these ones with the numbers, these are all asteroids. 5, 5, 3, 5, and Frank. If you're famous, you get an asteroid named after you. My advisor has an asteroid named after him. Dr. Whitney has an asteroid named after him. I'm trying to get on that list, you know what I'm saying? So only goal in life is to have an asteroid called Chris Money. We'll see. It will be, of course, much smaller than any of these. Look at the big numbers here. Here's 25,143. I don't know how big that is, but it's only a couple hundred meters across, right? Okay. I can't go visit it. I don't own it. It's just named. All right. Okay. What's this on the bottom right? Those are comets. What tipped you off that they're comets?
Well, I recognize the name.
Oh, okay. You know the words, so you can figure it out. Anything about the shape or colors or anything like that?
Like it's like.
Yeah, remember when we made those things and the steam was coming off them? Kind of looks the same, right? Kind of cool. These ones do look like two rocks together, and we'll see that more when we see 76 CG. So, oh, it's not even on here. Doesn't matter. Oh, there's our series with the little. We rotated around it. We had a spacecraft go there called Dawn. I don't really know what they found, but they found some surface ice. I guess that's cool. I don't care. Okay. So the asteroid belt lives in between Mars and Jupiter, and it has some special ones. These are called the Trojan asteroids. They live on both sides of Jupiter. They have the same orbital period as Jupiter, and they're shepherding, just like one of the dogs that shepherds all the sheep. Same thing that happens here. Okay. If you look here, this is on the horizontal. This is the orbital period in years. Earth is 1. That's where we live. The number of asteroids is shown vertically. No asteroids where we live, basically. That's good. Right?
Yes.
Why is that good?
We don't die.
We don't die. Okay, good. Mars, there's a few. Right? If you look really close, there are some numbers here. It's not so bad. Then there's like a weird spike here, and then there's a dip, and then a big spike, and then a dip, and then a spike, and then a dip, a spike, then you see what I'm saying? Kind of weird, right? Why? Yeah, why the dips? Why isn't it smooth? Why doesn't it just go? What's that?
Are there like rings of asteroids?
That's what it looks like.
The bigger ones pull the smaller ones.
The bigger ones, the small ones. I mean, how big was the biggest one? Remember, the biggest one was, there's only one of them.
Yeah.
The rest of them were real small.
They all colliding into each other at one point? That's the one. Fairly small.
They're definitely made small because they collide into one another, but that doesn't quite explain why there's gaps. What do these numbers mean?
That like one fourth of the comets and one third of the comets. It keeps getting bigger until it gets to one and stop.
Okay, so this is 0.25, this is 0.33. What's 2/5? 0.4. 3/7.
Almost half.
It's more than half. Right? Or it's a little less than half? No, it's a little less than half. A little less than half. Okay, then half and 2/3. The numbers do get bigger, you're right. Does that mean anything?
The amount of asteroids. Comes forward.
What happens here?
That's the last chunk.
Are two arrows pointing at anything? Yeah.
Is it like how the asteroids are affected by Jupiter's gravitational?
Right. Jupiter's big, right? Okay, so what would that do? Why would it mostly affect these ones and not everything? Well, these are the closest. Right? This is 1 to 1. What does 1 to 1 mean?
You're on
They
top
feel
of it.
all
The orbital period in years. Jupiter's orbital period is here, and this is the same orbital period, 1 to 1. So if I go over here to 6, this is like 12, I go to 6, 1 over 2. What does that mean?
So they're like an orbital resonance with the belt and
Oh. So if I look at these numbers here, I see these are multiples of the different orbits. So for example, this one here goes around twice for every time Jupiter goes around. If I go all the way down here to 3, 3 times 4 is good. Yeah.
You know, that's the-
Yeah, so down here, you're moving much faster, right? And here, you're moving slow, like Jupiter does. Okay? So every time you go around here twice, Jupiter is in exactly the same position as it was when you started. All right? And we already said that that's a problem, right? This is why there's gaps in the disks. This is why Io gets flexed, right? Orbital resonances add energy to those locations. If you're a tiny baby rock, and you keep getting pushed by Jupiter, you just clear out. Make sense? Okay, so that's correct. Okay. So it's like Saturn's rings, but it's around the sun and it's not as pretty looking. You've seen, has anyone seen Star Wars? Okay, and you fly through the asteroid belt. Accurate or inaccurate? Inaccurate. Why?
Too many.
Too many what? Too many asteroids per unit space. Right? Most of space is empty. You start flying in your rocket, you do not have to navigate until you get near a planet. And even then, you probably don't have to navigate. Planets are small compared to big spaces. Um. This one's fun. Here's Jupiter. These are all the different groups. These are called Hildas. I think this is gonna play. I hope this is gonna play. These are the Greeks. The Trojans in front are called the Greeks, and the ones behind are called the Trojans. Nope, it doesn't play. God damn it. Okay, hold on a second. Here we go. Okay. Why are the gaps in the top part, but not in the cartoon on the bottom? That I claim in scientific. Is it A, the cartoon is drawn too small? If it were drawn larger, we could see the gaps. B, the orbits are elliptical. Their location is chosen home. The cartoon can occupy a resonance location even if their average orbital distance does not graph. The cartoon shows a two-dimensional representation of the three-dimensional space. Now when you're ready. Vote on 3, 2, 1. That's too many numbers. That's too many. You want 2 answers? Okay, well, I'm gonna turn to your friend. See if you can get the answer out of that. Ask behind you too.
And at the same time.
Oh, that's your answer.
Yeah.
Oh, interesting. Did you think about this, or did you just talk about it all?
Well, that's fine. That's all
Hey, folks, what do you think? We ready to revote?
Yes.
Let's revote on 3, 2, 1. This is the first time everyone has changed probably their answer, and all of you got it wrong. So walk me through anyone's understanding.
What you said that? Oh.
Point this is anyone.
You said that everything's really far away.
Yes, yeah, that's
And
true.
so why picture it looks like it's really close.
Okay, yeah, sure.
You like me. Either
Well,
way.
I told you if you're flying through it, that you wouldn't hit an asteroid. But that does not explain why there's gaps in the top graph and not in the bottom.
Like, you zoom in, you see.
Even if you zoomed in, you wouldn't see them. That's my argument. So 1 is incorrect. So if folks are thinking 3, they're like, oh, I got it now, right? What's 3 mean?
It's same energy, like up and down,
Up, down, right? So the gaps like
like
don't
Like,
exist in 3 dimensions.
off like a
Baklava?
layer.
Like a layer. Oh, layers. No. Okay. So why is it this one? What the hell does that question even say?
Didn't understand it, so I didn't make it.
Okay, and no one wanted to clarify that part, right? So it said asteroid orbits are elliptical. Is that true?
Yeah.
Yeah, generally speaking, sure. Their location at a chosen moment, the cartoon, can occupy a resonance location, even if the average orbital distance does not. Average orbital distance, what is that? From what? The sun. Okay, the average orbital distance from the sun. That's also called. That's the unit. So you have average distance in AU up here at the top. Right? Didn't we say there's a relationship between the period and the distance? If you're closer, you have to go faster. If you're farther, you have to go slower. Okay. So even if your average distance here is at one of these locations, you can at one moment hang out in any of these locations. So it isn't like we look at Saturn's rings and there's clear gaps in it. Does that make sense?
That was an instantaneous picture, the other one's an average.
Yeah, this is an instantaneous picture. This isn't even an average. This is saying the average distance. These are properties of them, right? Right? Okay, here's an example. Okay, it's really hard to see here, but I promise this is happening. Follow the red dot. You see the red dot? Yeah, sorry. Okay, hold on. Let's go back. Can you turn that light off again? All of them. This one's gonna take a real focus. Do you see the red dot? Okay, this is inside of the asteroid group, the Hildas. Okay. Oh, now watch it go around. See how sometimes it gets closer, sometimes it gets farther? Cool, right? Maybe cool is a strong word. Okay, lights on. So we did talk a little bit about the size frequency distribution. We said there's one big one, Ceres, and there's not a lot that are like as big as Ceres. There's some other ones. There's like Vesta up here, and there's like Lucia up here, and then there's the small ones, and there's lots of the small ones. All right. So this shows the diameter here and the number of asteroids here. Does it look like anything to you? Good. Yeah, it does look like a pattern. What pattern does it look like in nature?
Isn't it like when, like I guess, asteroid that's
What do you mean?
like you showed us that one graph where it's like bigger, the bigger the asteroid, the more impact it'll be to like basically killing your.
Right. So the ones that kill us all, do they happen frequently or infrequently? Infrequent, thankfully. Right? If they were very frequent, we would all be dead all the time. And in fact, it kind of makes sense, right? Because there's not a lot of things to kill us. There's a lot of stuff that burns up in our atmosphere that's very small stuff, right? And that's exactly why.
Oh,
I'm supposed to lay it on top. Okay, I guess we're gonna do comments really quickly and we'll come back to that thought. Any questions before we go to comments? Okay, comments are cool. That's one. It's a real picture. That's like snow and stuff, and that's okay. Comment. Okay. Here's the different parts. We saw a picture of nuclei, and we saw the zoomed in version with Vesta and with Ceres and everything else. But mostly what you see are these two tails. So the nuclei we'll see in a lot of detail. We're going to leave that away for now. The coma is this gas atmosphere that happens as the surface sublimates water and CO2, ice, and CO, ice. That makes this atmosphere, it's very tenuous, it's very thin. And then some of it becomes ionized and it gets swept away by the solar wind. Also, that atmosphere, as it boils off of the surface, it drags with it small grains of dust. And the dust is very reflective. So that's what you see when you see a comet. You're seeing just dust in space that's reflecting sunlight. Okay? The thing is that these extensions of the coma point away from the sun. So if you made this picture, I hate this, the chalk in that. Okay. So you made this picture, right? Then here's the sun. And then I'll put a comet here, comet here, comet here, comet here. Alright. Which way does the tail go here? It's really far from the sun. No tail. Okay, so just like. Check. Give me away. Okay, what about here? Away from the sun. Make it longer. Let's wait. Here? Longer. Yeah, now longer. Oh my god. Okay, and here?
Longer.
Longest. Oh my god, it's not even believable anymore, Mateo. Your perfect drawing. Okay, what about this one? This way?
Could be the same as the one on top.
This one? Do you see the difference? It's not pointing this way, right? Yeah, there you go. Okay, let's do it that way.
Oh, okay. Okay, good. Thank you.
This one? The mole? Yeah. Okay. Which way does the dust go?
Which makes the comet movie?
Dust tail follows the orbit.
I like it. Trying sometimes.
Yeah, so they're gonna look like this. Here. And then here.
Same, like on orbit.
And then here. Like right angles. What the heck? This thing's drunk. Oh no. All right. Make sense? Okay. It looks, the plasma tail always looks straight, whereas the dust tail will look curved. And the one that you'll see will be the dust. You can see the plasma if you have a nice instrument or a nice telescope, but more than likely you're just going to see the dust tail. Okay. Questions? Here's the ones we visited. There's 1P Halley. Do you want to actually hit the lights again? Thanks. Let's go, darkness. Okay. There's Halley. It's a bigger one. It's about 16 by 8 kilometers. And that's the closest we got with Vega 2. These are the ones that we've actually visited. We'll talk a lot more in detail about Rosetta. Deep Impact, I think, hit 9P Temple 1. No, both of them. Yeah, Deep Impact went to both of them. I don't remember. And Stardust is really cool. Flew by with like aerogel, which is like this really soft, very light stuff. And it picked up pieces of the dust grains and brought them back to Earth. Very cool. Okay, so let's look at this one here. Okay, funny shape, right? Here's it close up. What do you see?
Like an apple.
Looks like an apple? Yeah.
And
A Grand Canyon? Yeah, this is a hell of a canyon, that's for sure.
A new.
This looks like it's been nuked.
Like the mushroom.
mushroom cloud,
Here,
like
Kind of going up, yeah.
like this.
mushroom cloud.
Okay, all right, some jets on it. I'll call them jets, not a mushroom cloud.
No, if you turn it this way. No, yeah, it looks like a mushroom club.
Okay, I don't see it, but I see what you're saying. You're saying this?
Yeah.
That's one half of one thing. You don't even know what the bottom looks like.
Yeah, but just by the lighting.
It looks like
Okay, all right. I get it. What about any like geologic features or like, part of the class, Impacts.
Yeah.
You see impacts. Okay. If you think about what it would be like to lick,
rough.
rigid, rough, crunchy, crunch taco.
Oh, wow.
What's that? This kind of looks soft to me. This looks like velvet,
I mean,
like ice cream,
I was gonna say like up there too, like
right?
like at the top.
Even up here, this looks really soft. Right?
Is it
Well,
like space like
kind of like-
granite?
Yeah, what is that? All right, let's rotate it into view a little bit more. Okay. What? You don't think that's the same thing? Sometimes you look at something slightly different. It shows you a new aspect of itself. Okay? What's this up here? What's this at the top here?
Crater.
It's a crater. So there's enough tensile strength here that we can leave craters intact. But it's smooth in other places. It's very smooth here, right? Is there an atmosphere? Huh. Why is there an atmosphere? Is there volcanism? No, but you said there's an atmosphere.
Hot space rock.
Hot space rock. Why would hot space rock make an atmosphere?
Not an atmosphere, but they don't.
Ah, so remember, it's not a rock. It's an icy rock. So as the surface begins to melt, it does create an atmosphere. Is this causing erosion on the surface? No, it's very tenuous. It's very thin. So what causes it to be smooth like that?
Probably flying. Solar wind. Wait, solar wind isn't like. I don't think that.
Crater impact.
There's no air in space.
What happens when you, for example, okay, you just got food at Taco Bell, okay? And you put, like, you got a Baja Blast. You drink all your Baja Blast, and you look at the bottom, and the ice is still in there, but it's all fused together. What happened?
The moisture got sucked out of it.
Well, you drank the Baja Blast,
Yeah.
but why is the ice stuck together?
Well,
It froze together. So the Baja Blast was warm, the ice was cold, and it melted and it stuck. So ices can form, they can melt and they can reform. They melt and they reform. They melt and they reform, right? So here I have ice on the surface.
Does it like melt when it gets close to the sun and then reform as it goes along?
Oh, that's exactly it. So the reason it's smooth is because the ice, even if it had all these different shapes in it, once it gets really hot, the whole thing melts down and becomes flat. Right? Well, flat in space. Smooth, I'll say smooth. So that's the size. This is why we don't want it to hit us. Yeah, that's me right there. What? Oh shit, it's your boat. I'm just kidding. So it doesn't look like a mushroom cloud anymore, does it?
I mean.
Oh my gosh. Don't look for it on purpose. Okay. Yeah, so this is us. This is why we don't want it to hit us. Okay, hold on. So now I have to switch slides, I think. Yes, let me switch slides really quickly. Oh yeah, it's in here. Let's go. I'm almost caught up. We're gonna get it. Oops.
so 1,000.
Enable.
Some comments eventually disappear. As they.
Very good question. Why don't we think about that?
Think about it.
Let's think about that. What happens every time a comet comes close? It gets smaller. So are there comets that have existed since the beginning of the solar system? No. What's the lifetime of a comet? How many times can it pass by the sun? Depends on the size. Well, we saw how big they were, right? Do we think they are as big as a planet that are just lurking out in space? No, probably not. They're the leftovers, but they're the icy leftovers. Okay. This is a great example. This is called should I forget the name of the comet? I think it's the McNaught comet. And that's a real picture that someone just took with their camera. It's very cool. So if you want for scale here, right? This is like, if you look down on the sky, it'd be like 15 degrees across. Absolutely massive. And you can mostly see them like, this one was low on the horizon. But if you have the right orientation, They will be absolutely visible in the middle of the night. Really beautiful. Okay. Let me show you some cool comets. Okay. So we visited 67P, Cherymove Gerasimenko. So that's the one on the left and the one on the right. They found this, they're friends, not together. And that's what it looks like. Yeah, beautiful.
That's the same one we saw earlier.
Yeah, same one. And you can see all these jets coming off of it. And you'll notice that the jets are coming off of the illuminated surface. So there isn't jets coming out of the dark. They're coming out of this side, right? Okay. So from the image on the bottom, this is the bottom image. We saw that already, right? How old is 76P CG? We're ready. Let's vote on 3, 2, 1. Okay. I'm gonna have to separate you two. What do we think is a reasonable argument? You think 4.5 billion years old? Age of the universe? No, why not?
It's probably way smaller than four. That would be gone.
Okay, so you think that it's gone by enough that it would be gone? Good, but that's not using what we provided. That is true. That is a perfectly good argument. So we could throw this out as a red herring. Because we just had that discussion with Kat. Right? What about this one? Can you tell from these images?
Yes.
Yes, you can. So this is another red herring. So it's within these. Anyone want to defend any of these? Yeah.
Is it 4.5 thousand because it's 4 kilometers wide from the asteroid, then if you just like follow the graph right up there, you just cross one whatever.
So you want 4 kilometer comet. Then you want to go here to 100 million years. That's not quite it. It's certainly using this graph, but it's not exactly what we wanted to go for. Yeah. So what about measuring the crater size? How big is the big crater there? This crater is 4 kilometers. Remember, it's the crater that we're caring about. So here is
If it hit.
What?
I don't understand what's happening.
okay. So look at the size here.
Yeah.
The whole comet is 4 kilometers. How big is the crater on the comet? Remember, this is how we date things. We look at the craters on the object. If it has lots of craters, we know how old it is. So there is a crater right here. How big is it? 0.5 meters.
Wait, wouldn't it be 4 decades?
And this is 4,000 meters or 4 kilometers.
What are you doing?
Yeah, either 1 or half a kilometer. Okay. Estimates are fine. I'll say 1. 1 kilometer. 1, 2, 3, 4. Boom. Okay. The whole crater is 1 kilometer. And then you're right. You said we should look here. The crater is 10 times larger. So the impactor was how big? 100 meters. 100 meters. And how many of these large craters do you see here? This 1 kilometer crater? Just one. Good. So I don't have to scale this at all. Right? I can use what's up here. So I go to 100 meters and I go up here, and this number looks like 4,000 years. Here. Does that process make sense?
Yeah.
Was that intuitive?
I thought now that you explained it, I understood.
Okay. That'll be on the homework then. We'll do another one. Oh, damn. Okay. So we saw that picture, we saw that picture. Okay. So when we look at the images themselves, we have these wonderful instruments on board. You can see the visible images. You can also see where the ice is and where the temperatures are warm. So white is warm, red is not so warm, black is dark. Dark is cold.
Black is dark.
Okay, too much vodka. All right, and then over here you don't have very much ice. In the places where the ice is warm, that's where you're going to get the sublimation. Okay, so here's how the process works. During the day, sunlight heats the ice, and that heat penetrates into the ice, melting it. And so that turns it into gas, and the gas can creep through and escape. Those are the jets that we saw. And then at night, it cools down and it refreezes, right? And in the morning, it starts all over again, starting from the top and working its way down, melting the very top layer and penetrating lower and lower. Straightforward?
Yes.
This looks funny. This won't be on any exam, but this is hysterical. Okay, so the Rosetta group also brought with it a lander. They wanted to land on the surface of this comet. And what they're gonna do, the comet is made of a porous material. So think like the rocks that you like rub your feet with if you have calluses. You know what that is? Yeah. So that type of like porous rock. And so the problem is like if you imagine landing on it, you have to make sure that you don't like go through it or like bounce off, because then you'll never be able to get back. So they installed like a giant hook. And they were going to shoot the hook into the ground, like hold them into place. Pretty good idea, right? And they're going to land right here. And they just want to hang out and like look around, like take images and let you know what the surface of the comet looks like. Okay. And that's what the surface of the comet looks like.
Is it snowing?
Yeah. Why is it snowing? Because it's ice and dust being liberated from the surface, right? As the gas sublimates, it releases all of this gas and dust. Look at these cool rocks. Isn't that cool? Yeah.
So is the snow different on there compared to like yonder?
Yes. In every single way. Remember, there's no atmosphere here in a meaningful way. This is not falling. This is just dust moving around, snow moving around. It's like being in a storm, but there's no pressure.
But only the foreground is the snow, right?
Excuse me, say that again?
Only the foreground, the stuff in the foreground is the snow?
We're talking about all this too.
That's snow too.
It's like dust and water ice, yeah.
The stars.
No. This is all like atmospheric coma, dust and ice. This here, yes, also what you would consider snow. These are rocks, and then this is a cliff edge. You might be saying to yourself, how did you get that really cool image? Let me show you. So it's flying, okay? And it's going down, and it bounces, and then it fell over into it. I know, it didn't work. And where it landed, it happened to land in that, like, here's a cliff. So it landed on the edge of the cliff. That's the only reason it stopped bouncing. Okay, so that's where it's supposed to land, and that's where it landed.
That's pretty close.
You know, okay, so we had an argument about this. So I have a friend, he's Italian, and he's a big fan of the European Space Agency, right? So these are all European Space Agency like works. And I said, you know, this is a failure. Right? He said, well, no. Technically it did land.
It is.
not where we wanted it to. So technically a success. I said, okay, whatever you need to get through your day. So what's the problem with landing in this cliff?
Not visible light.
No visible light. So it landed in a dark area. And all of a sudden, the solar panels are like, y'all, I'm not doing good. And so it sent some pictures back, but then it just died.
How long did it last?
Oh yeah, it's definitely still there. Yeah.
How long did it like, but it's staying on?
Like a couple hours.
But it's like moving, it's a moving object at some point, would it not get sunlight again and maybe turn on?
Yeah, I mean, I think the orientation is like this. Cliff walls like this, and the solar panels like this. I don't have a way to like orient it. So it gets some amount of light, but like depending on how it's oriented, not enough to do anything with.
I thought it says like, they didn't have solar panels.
At this comet?
No, like, like for the little spacecraft.
Yeah, so which spacecraft was that didn't have solar panels? New Horizons, and that went to which planet? Pluto. And where did we talk about this being? We didn't. We didn't talk about where this is yet. Right?
Right.
In fact, water starts to sublimate from the surface at about 2 AU, so a little bit past Mars. So in fact, there's plenty of sunlight. And we know there's plenty of sunlight because look at how nice the surface looks. Right?
So
It's close, yeah, relatively close. But good thinking, right? If we had just thrown a little nuclear reactor on there, bada bing, bada boom. Of course, we would have melted all the snow with the nuclear reactor, but that's fine. Different
yeah.
problems. Right? Okay. All right, and so these are some of the pictures I took. I mean, that looks pretty cool. A little chossy, like I wouldn't rock climb that, but it's pretty good. You know what it means, chossy? Choss is like you put your fingers in there and then you pull, it'll like break. It's not a good handhold. It's like granite isn't very chossy, whereas like sandstone is like the material composition doesn't have structure to it. Does that make sense?
Like a pile, like
It's crumbly, yeah. But so the way that you look at it here is like all of the lines here, they're like in granite, it looks like one face. Whereas here you can see all of these different veins through it, so you know it's gonna crack. Okay, that's it. You know now know about comets and asteroids. What's the nucleus? Small in the middle thing. Good. What's the coma? Dusty, gassy outside. What are the two tails that it has? Dust and plasma. Good. And they point away from the sun. Good. Okay. This one's carried by the solar wind, appears straight, and then this one curves outward by sunlight. Appears curved. Okay. When you study cometary science, which was the first thing that I tried to study in graduate school, my first comet, it's kind of like this. Went in and was supposed to go really close to the sun. It's called a sun grazing comet. And we were supposed to watch it on its way out. We would take all these observations with our telescope. And it was Thanksgiving. I put the turkey in, having a nice day. And then I'm like watching the updates from the live cameras. And I see the comet go in. And it never came out. So you know, they say the thing about studying comets is they have tails, they're like cats, right? They have tails and they do whatever they like. So sometimes you want to go to observe them and they're just dead. So they've exploded. I'll show you images of that on Monday. It's really cool because they get really close, totally break up, and then evaporate. Okay. Questions about this?
I'm so sad.
Okay. Fate of the comet. Comets lose about 1% of the mass with every pass by the sun. So you can only orbit a few hundred times. So we saw that Rosetta was looking at a comet that was only 4,500 years old. Pretty new. Right? They can become rooted in too much dark stuff, and they'll start to look like an asteroid. So there's this whole spectrum that goes between icy stuff to rocky stuff. Some of that's called centaurs. You'll never learn about them, doesn't matter. They can also break apart or disintegrate. So here's the nucleus here, and here's these pieces, these chunks that have fallen off that are also now starting to disintegrate. They're also starting to put out little comas of their own. You see all this stuff? It's good, right? And then sometimes they do smash. We did that in the last lab or second to last lab. We saw, they talked about this Shoemaker-Levy, which is a comet that hit Jupiter. And this is the image of what happened when it hit Jupiter. So you see all these dark spots. There's not impact craters because obviously there's no surface on Jupiter. But this comet, as it was coming in, broke up, and then each of the pieces smashed into Jupiter and left these big scars. So kind of cool, right? Okay. Oh, I put one in. Look at this psychopath. Okay, so this is the sun, and we put on top of it a coronagraph, which blocks out the brightness of the sun. So you can see cool things like this is a solar flare coming off of the sun. But you can also see these comets just going towards the light like a moth towards the light. Like, whee! These ones have very short lives, maybe 10 or 15 times going around the sun. Has to go really close. Some of them go, I don't know how close this was. Some of them go like 1 or 2 solar radii away, which would make their surfaces, thousands of degrees, but only for a little bit of time when they fly off. Pretty cool, right? Okay. So where do comets come from? Well, we saw these KBOs. That was the first place we started. That's right in here. So this is like Pluto's orbit and all of these KBOs. Right? And you say to yourself, oh, that's probably where they come from. But a weird thing happened. Started looking at comets, and they look like they come from every direction. And so there was a Dutch astronomer, I forget his first name, but his last name was Oort. And he saw 3 of these comets, and he saw they were coming from random directions. And he was like, hold on, I can figure this out. And he did some math, and he was like, I think there's like 1 million objects in like this cloud around us. And off of like 3 objects, he got it right. What? So apparently, you go past the Kuiper belt, and there's this big halo, spherical halo around the entire solar system of icy bodies. And for the most part, they don't move very much. They move very, very slowly. But every once in a while, they get bumped, either by a passing star or by something out in the solar system. And they change their orbit and they head in towards the sun. And they can only do that a few hundred times, right? So if this happened to all of them, that would be gone. But in fact, most of them, millions of them, are just out here hanging out. Isn't that crazy? So all of this fits into big thing right now. Okay? Make sense? What?
So
Yeah, this is the crazy piece. So we haven't even really gotten outside of our solar system yet. Yeah. So these Kuiper belt objects, the ones that we see from like Pluto, sometimes these do come in. Those are called Jupiter family comets, whereas these ones are called Oort cloud comets. And the reason they're called Oort cloud comets is because they're from the Oort cloud, right? That one's an easy one. Jupiter family comets is mostly because they're kicked around by Jupiter, and they're usually kicked in, and then they, come free for us for a little while, and then they get destroyed. Okay. So Oort cloud comets are long-lived, mostly because it takes like 10 million years to go from here to here, and then they fly back out again. So the other comet that I studied in grad school was called Comet Sighting Spring. It was a new Oort cloud comet. And I think it took something like 12.6 million years to go from out here where it started on its very first time in, and then all the way back out. And you say to yourself, how do you know it was this first time? That doesn't make any sense, Chris Money. Well, interestingly enough, it comes in, right? We watch it, we see it get close. So at about the distance of Jupiter, we can start to spot them for the first time. And we say, there's a comet. We find its trajectory exactly. And we can say, okay, we watch its trajectory as it goes through the inner solar system. It does that, it goes all the way through the inner solar system, and we watch it leave, and we say, oh, how much energy does it have right now? And it has the escape energy for the entire solar system. So it's coming in and it's leaving and it will never come back. As it came in, it bumped into too many planets, got gravity assists, and left. Isn't that crazy? But one and done. Okay. There's the Kuiper Belt, flat and wide. That's just an example of the different things we've sent through it. We sent Voyager 1, Pioneer 11. There was New Horizons. So once you're out here, you definitely need solar panels. Sorry. What's the opposite of what I just said? Notice here, Pioneer 10, no solar panels. Voyager, no solar panels. Pioneer, no solar panels. New Horizons, no solar panels. Voyager 2, no solar panels. Voyager 1 and Voyager 2 currently hold the record for farthest away from us things that we made. New Horizons holds the record, at least until Bepi Colombo launches, of fastest thing that we've ever made.
What is that one?
Bepi Colombo, I think it's 2024, unless I'm dumb and it's this year. It's very possible. New Horizons went by Pluto, and I think it went by MU69. So MU69 was another object that we found. I think they renamed it. And I'll show you some pictures. What did I show here? Okay. Okay. Yeah, here's the object. Kuiper Belt object. So this is called Arrokoth now, MU69. So these are the images it took as it got closer and closer. Pretty interesting, right? What does it remind you of? What? A snowman? You want to build an Arrokoth? Sure. No, but if you look at it closely, right, you have these like lobed features. Does that look at all like that comet we saw?
Yeah. I see the new one.
You see the nuke cloud, right? Because they had this little piece in the middle. And the piece in the middle that was the part that was connecting where the gas and jets were coming off, right? Okay, and as we got even closer, you got this image, right? That's really good. And then these are the final images we got.
Looks like rotten.
Why do you think it's potato? It's not a potato. This is a real image. You don't think this is real?
Yeah.
Raise your hand if this is a real image. That's my dad. No, that was a joke. But it kind of looks funny, right? It does look like two potatoes grown together.
Why is it like that?
Yeah, that's a very good question. Why does it look like that?
Like it looks not rocky.
Yeah, it doesn't look rocky. It looks very smooth, right? Why is it smooth? Right, it's icy, remember? So the surface is very icy. There's not tectonic features giving it cracks and whatnot. There certainly are places in here, right? So that looks like it was like smashed in. And you can kind of see it here, right? It's kind of smashed in there. But it's smooth, it's relaxed. And all of these large pieces here, they're compressing under the weight that exists. But they're also not experiencing a lot of other impacts. There's not tons of impacts messing this up. Because they're so far out in the solar system, there's nothing really to bump into. You're moving very slowly. The smashes into one another are not very energetic. And so now you say to yourself, why is there one and then another one? Exactly right. You have two objects here, big one, small one, they were hanging out, besties, right? And then maybe they're rotating in a funny way so that their rotation eventually gets their orbits to fully decay. And they just stick to each other. And say, let's be friends forever. The moon's doing the opposite of this. The moon and us are beefing. Okay? So the moon used to be really close to us. And we said some mean things about the moon. It said some bad things about our mom. And it has been moving away slowly at about 2 centimeters per year since it was first formed. Now you say to yourself, 2 centimeters a year, I could grow a lot if I was 2 centimeters a year. That would be a bit like, wow. But 2 centimeters a year, not very much in astrological time sense, right? But in tens of millions of years, it will be much farther away from us, right? In billions of years, we won't even have them. Crazy, right? Okay. All right, there's the moon. Let's do, we have to, okay. What? Okay, why is there a meteor shower every year around August 12th? Okay, here's the meteor showers, major meteor showers. Here's the approximate date that they always happen. Right in there is my birthday, just keeping in mind.
What is it? May?
Oh, okay, comets only enter the solar system on certain years.
No.
Comets only have a 1-year orbital period. Earth. Give all the answers away. Earth passes through the orbit path of the comet at the same time each year, or D, none of the above. Let me know when you're ready. We're connecting all those things today. We're going to connect them all, and then next week we're going to talk about formation of the solar system. You're like, ah, I got it.
Yeah.
Let's go.
I don't know that.
Ready? 3, 2, 1. Okay, that don't look like I tricked very many people. Anyone want to give their explanation?
The Earth clues are in there.
Okay. So you said 3 or C, that the Earth passes through the same place. So the comet goes in, leaves dust behind, and then the comet leaves. And then we pass through where it was. And that's why it happens at exactly the same time every year. Isn't that weird? Yeah. That's it. Pretty cool. Okay, so meteor showers are caused, hopefully I've said this enough times that you remember. They're caused by dust that escapes comets. And then hits the top of our atmosphere and it burns up. Okay, that material spreads slowly in the direction. Okay, so here's the nucleus moving that way. There's the sun. So first it gets liberated from the nucleus, and small grains, okay, they go like this, like that. They fall backwards because they're getting pushed by the sun. Did you know you could get pushed by the sun? Called the radiation pressure. So you kick these tiny grains, and because they're so small, they're like, wait. Okay. But the big grains, they're like, I don't care. So they just sort of lag behind the nucleus. And they form a dust torus. Or just like think about a long pool noodle filled with dust that's coming behind the nucleus. Okay? And then we fly through that dust noodle and we get a meteor shower. Cool. Okay. We did this. I think I did this out of order. Probably. Okay, here's this thing. This is what I meant to show you. Okay, so I claimed that this explains something. And David helped me, right? So I could do something like that. I can turn this thing around. I can say, here's the impactor size. Here's the current impact rate. And I say this piece should be over here, 100 kilometers. So let me like flip that other one and turn it around good. Okay. And there you go. Impactor size, typical time between impacts. So small impactor sizes up here happen every year. Big ones, once in Earth's history. And that makes sense. There's only a few objects that have this size, right? What happens when they do hit us? We did. Yeah, not good. Okay. So we do know what happened. We've seen what happened. We have evidence of what happened.
I'm not gonna see what happened.
Oh, yeah. We're not personally going to see. So after the planets formed, there was material left over and collisions were frequent. We can see this in the impact history of the moon. We see there are large periods when all this stuff was hitting at the same time. So how could you tell? Well, you can look at different surfaces and find out how old they are. And you look at each surface and you see how cratered that individual surface is. Does that make sense? And you can compare different aged surfaces, and you see that the older craters are much heavily cratered than the younger craters. That seems counterintuitive, but I promise it's not. Okay. Probably this is why the water in front of you tastes so good. This is comet water, probably icy asteroid water. It's kind of fun. You're like drinking an asteroid. So what happened was the surface of the Earth was molten lava, and unlikely that the oceans that we drink today, that we swim in, came from the interior of the Earth. We found the water from the interior of the Earth doesn't have the right chemical composition. So instead, we think after the surface formed and was hard, crusty, it got smacked a lot by asteroids. And those icy asteroids, those comets, just left their water here and it turned into an ocean. Yeah. That's what I'm saying. It's a lot of smacks.
Like possibly we can't see anything,
What?
like we can't see anything too significant because it's covered by the water.
Well, you wouldn't see those anyway because usually oceanic crust is very new. Right? Remember, it gets recycled very easily. Yeah, but good thinking. Okay. So what's going on here? Why are these all weird? Well, we know which one's alive and which one's dead, but why? So this one we understood Venus, right? These two are roughly the same size. One is all core and the other is all mantle.
Mercury got beat up.
Mercury got beat up. Okay, that's a thought. What about the moon? How'd the moon form? From the Earth, like the rib, right? Okay, what do I mean by that? Probably the Earth, very early on, was struck by something about the size of Mars. Okay? That hypothetical object is called Theia. In that process, instead of hitting straight on, it hits at an angle. And it smashes into the Earth and rips off the mantle and throws it into space. All of these pieces that later coalesce into the moon. And this happens very quickly, on the order of several days. Yes. So here's Theia smacking into us. We're spinning, we're having a good time. We're not hurting anyone, minding our own business. Okay? Bam! Smacks into it, huge amount of energy. And importantly, it's going to do something to the mantle. The rocks that leave are going to have a lot of heat in them, and it's going to vaporize out really important chemicals that are not present on the moon, that are present on the Earth. Okay? And it also tilts us. Thanks, now we have seasons. Ugh. Right? Could have had a great California with no seasons. Sick. All right, whatever. And we get a moon.
They hated us.
Who? Yeah, Theo was like, not about it. Okay? And the moon forms from the debris. And we know the moon formed from our debris because we went to the moon, we picked up the rocks, and we're like, these are Earth rocks.
Imagine.
They look exactly. Well, no, it's great. What an amazing story. You're like, this is formed from the mantle of the Earth? That's crazy. Oh my God. Right away canceled. Right away canceled. Okay, so they said, well, can we simulate this? So this is called a smooth particle hydrodynamic simulation, where if you like the fluids class, this is like fluids on crack. So this is going to do every single particle, and it's going to represent like a fluid. And as we smash into these two objects, so this is Theia and the Earth right before impact, and then it's going to smash into it, it's going to spin it up. Okay. Whoa.
So it renders every particle?
Well, within reason. Yeah. And see, here's our proto moon. You get all these little moonlets, and this will eventually form into the moon. This is pretty cool in the day, right? This is like, I forget, this is early 2000s. People were like, wow, computer. You know what I'm saying? What was that? Okay. So this explains why the moon orbits in the same direction as the Earth rotates. That's interesting. I never thought about that before. It also explains why it has a lower density than the Earth. It's all mantle and it's the Earth's mantle. very little bit of its core left over, that's okay, we don't care. And has very little easily vaporized stuff. There's no water in the crust, there's very little oxygen in the crust. So we know, okay, that stuff was all removed in this part. See how hot it is in here? 200 degrees? All that stuff's gonna be vaporized. Right?
The way Thea was presented in the picture, the Joe, was it like another movie? It's kind of
It's about the size of Mars.
like, so it's a planet, or it could be another movie.
Well, it's not a planet, because it doesn't form the definition of a planet, right?
It's spherical.
But that's not a definition of a planet. We need a lot of things, right? What are the three things we need? We need spherical, orbiting the sun,
And it has to have space cleared out.
it's space cleared out. So it didn't clear out its space because it hit us. We were in its space and we were in a planet and it wasn't a planet because we were in one another's space and so we smashed. Does that make sense? Okay. And that's like what is this? Is this gonna go? Yes. Okay, so this is an updated simulation. So cool looking.
You just all happen in like a couple of days.
Yeah, look. Few hours. Look. That's the moon problem.
So we have children there.
Not beautiful. I could watch these over and over and over.
That happened so fast.
So it explains a lot of things that we've seen. We're gonna use this as a catch-all for understanding planetary formation. If we don't get something, we're probably just gonna say, well, it's probably got smacked. Just because it's easy. It explains why Uranus is probably tilted. It maybe explains Venus. Venus is my favorite hypothetical answer that we cannot answer. So if you want to hear like a weird science thing, this is like what the limits of science allows us to think about. We form the Earth, we have the moon. Okay, they're both rotating in the same direction, and the moon rotates around us. As I mentioned before, it's getting farther away from us. Okay, that's because of an interaction with our tides. However, if you formed the moon and then you smacked us again, and you rotated us, say, in the other direction, now that first moon would come towards us instead of going away. So if we had one moon and then another moon, and they're moving towards us, they would just smash into us, much like potentially Venus might have done, which would remove all the liquid, right? No water, no plate tectonics, and therefore build up of all the gases that we see. Now, is this provable? No. This is an idea that a very prominent scientist wrote he wrote it at a conference and he said, we can't do anything about this, but here's an idea that I had in case it's ever useful in 40 years. I like it. I think it makes a lot of sense, but who knows? Okay. Probably shattered Pluto into Pluto and Charon. That's probably one object, became two, and probably caused Mercury's large core. So we can imagine the same thing happening to Earth. It's hit from the side, removes that mantle, but now instead of forming into a moon, that just falls into the sun. Right? Okay, so this is tending to explain a lot of stuff, and we'll talk about the theory of the formation of the solar system on Monday. Questions? Okay. Let me give you back. David.
I feel super early.
That's okay.
I was like, oh no, everyone's be there. I'm gonna get there 15 minutes.
Kat?
Whenever I'm disappointed in myself, I call myself vegan.
Oh. Okay.
But now I'm, every time I hear it,
I don't know.
So that a more thing came from where?
What's that?
Where did it come from?
Where did what come from?
The long cigarette and more, whatever, I don't know. The one they were calling a spaceship.
Oh, that's just from another solar system.
So
You
that's
remember the one that-
beyond the Oort cloud.
Yeah, remember what I studied in grad school, the one that left?
Mm,
That's just gonna go into someone else's solar system at some point, right?
So something else pushed it over here.
Yeah, exactly. Okay. Yeah. One. One. Let's see. Oh, go on.
How many are you got?
As many as I have. When does your class start?
5:30.
Oh, God. Go quicker.
You're good. It's 5:18. You got that. Take that.
Yuri. Lucia. Kobe. Isabel. David.
It's still light outside.
Zori. Name? Random name. Okay, I don't know who that is. Zuri. Lucia. Lucia. Kobe. Kat. Andrew. David. Kobe. Oh.
By accident, a lot of
Abdallah. Alfred.
I haven't locked we've been.
Zuri.
That was first semester.
Right here.
Like,
Yes, yes. Dory. Eduardo. Lucia. Isabel. Trinity. Alfred. Trinity. Isabel. Nice drawings. Gonzalo. Andrew. And here. David. Kobe. And Zori.
Thank you.
Thanks for your patience. Sorry.
No worries.
You still have more time.